Hi, and welcome to AWS Innovate Conference. My name is Ekta. In this session, we'll look at analytics through the eyes of a business intelligence analyst, a data scientist, and a data engineer. We'll also explore how to quickly leverage Amazon Redshift, Redshift Spectrum, Amazon QuickSight, and Athena to create powerful yet straightforward business solutions. In this session, we'll start by looking at the current trends in the data-driven development. Then we'll look at some of the stakeholders in a data organization and how AWS ecosystem maps to them. In the context of these stakeholders, we'll look how service like Redshift is evolving from a traditional data warehouse and expanding its capabilities to handle more sophisticated data analytics use cases. We'll then discuss how to build advanced data-driven applications with Athena, Spectrum, and Amazon QuickSight for visualization. Finally, we'll see how Spark can be leveraged, and then we'll open the session for question and answer. And remember, this is a level 200 session. Before we dive deep into the session, let me quickly introduce myself. My name is Ekta Parashar, and I'm an Enterprise Solution Architect Manager based out of our Mumbai office in India. As a solution architect, I have had an opportunity to work with several enterprises in their cloud adoption journey. These also include customers. They have deployed their data lake platform and also migrated their analytics workloads to AWS. So let's begin. AWS provides the most comprehensive, secure, scalable, and cost-effective portfolio of services to build customers' data lake and analytics solution. Customers can store the data from any of the data sources in a data lake using standards-based data formats. They can analyze the data with the largest set of analytics engine from AWS and the most partner solutions that have pre-built integration, giving customers choice and ensuring that their needs will be met for the existing and future analytics use cases. As a result, there are more customers running their data lakes and analytics on AWS than anywhere else. As you can see on the slide, that there are various kinds of end users of a data lake who would want to consume the data for different purposes. We'll be taking few of these personas and understanding their need and how it can be achieved using various analytics services. While these personas are not hard and fast, but still a good grouping of categories of users. We can expect a single individual could wear multiple hats. We also want to emphasize that the flexibility AWS provides to match the use case to a broad and rich set of analytics tools. Contrast to a lot of other existing solutions that require a large capital expense that locks your future questions to previous platform decisions. Let's start by looking at the Bi Analyst. Again, let's just keep in mind that these personas are general characterization and may have significant overlap depending on whatever project you are working on. So what do Bi Analysts do? Just to level set, they spend most of their time analyzing the data to figure out market and business trends for companies with a goal to increase profits and efficiency. For example, they analyze past trends and current conditions and then communicate those trends using reports. A typical use case here is analyzing sales data for a retail company to optimize profits. For these types of use cases, like historical analysis, Amazon Redshift is a great platform for such workloads. A BI analyst can connect to a Redshift using three of the options. They can install either BI tools on EC2, which is our VM capability, and connect to Redshift. Secondly, they can use Amazon QuickSight, a very low-cost BI tool that connects to all your data in the cloud, including Redshift. We are working with our BI partners like Tableau, TIBCO, Jaspersoft to integrate Amazon QuickSight, and we'll discuss QuickSight in more detail in later slides. BI analysts primarily use SQL to manipulate data. With Redshift, they can extend SQL with new Redshift SQL functions and add custom functions via user-defined functions, also called as UDFs. Let's look at how Redshift is evolving from a traditional data warehouse and expanding its capabilities to handle more sophisticated data analytics use cases. Redshift has a massively parallel processing data warehouse architecture, which we also call it as MPP. Redshift automatically distributes data and query load across all the compute nodes to take the advantage of available resources. This means that all the queries are executed in parallel across all these physical resources. You can extend native SQL with Python UDFs or custom libraries. Python's compiled bytecode also runs in parallel across all your compute nodes. This horizontal scale-out architecture makes it easy to add nodes to your data warehouse and enables you to maintain fast query performance as your data warehouse grows. Another service, which is Amazon Redshift Spectrum, enables you to run Amazon Redshift SQL queries against exabytes of data in Amazon S3. With Redshift Spectrum, you can extend the analytic power of Amazon Redshift beyond the data stored on your local disk in your data warehouse to query vast amounts of unstructured data in your Amazon S3, which is your data lake, without having you to load or transform any kind of a data. Redshift Spectrum applies sophisticated query optimization, scaling processing across thousands of nodes, so results are fast even with the large data sets and complex queries. Redshift Spectrum can query using the open data formats you already use, including Avro, CSV, Grok, ORC, Parquet, RCF file, regex-serde, sequence file, text file and TSV. Since Redshift supports the same SQL syntax of Amazon Redshift, you can run the sophisticated queries using the same BI tools as you use today. You can also run the queries that span the frequently accessed data stored locally in Amazon Redshift and your full data sets stored cost effectively in Amazon S3. Let's take an example and get into some more details of Redshift Spectrum. It all starts when the Redshift Spectrum queries are submitted to the leader node of your Amazon Redshift cluster. The leader node optimizes, compiles, and pushes the query execution to the compute nodes in your Amazon Redshift cluster. The query plan is then sent to all the compute nodes. Next, the compute nodes obtain the information describing the external tables from your data catalog, dynamically pruning non-relevant partitions based on the filters and joins in your queries. The compute nodes also examine the data available locally and push down predicates to effectively scan only the relevant objects in Amazon S3. The Amazon Redshift compute nodes then generate multiple requests depending on the number of objects that need to be processed and submit them concurrently to Redshift Spectrum, which pools thousands of Amazon EC2 instances per AWS region. The Redshift Spectrum worker nodes scan, filter, and aggregate your data from Amazon S3, streaming the required data for processing back to your Amazon Redshift cluster. Then, the final join and the merge operations are performed locally in your cluster and the results are returned to your client. Another tool which is the key for business analysts is the visualization tool. QuickSight allows business analysts to visualize the data. To access QuickSight, you pick up your favorite mobile device or a web browser and connect through the user interface to our core engine. There's a data connector that's built into the product that automatically discovers and connects to all AWS data sources. As a user, you don't have to worry about how to connect with our data sources. Using JDBC ODBC drivers, you can also connect QuickSight directly to your data sources, even which are located in your on-premise data centers. We look through the data sets and build your data catalog using the metadata feature. Once you select your data source, you can start to visualize it immediately, or you can use our data prep feature. Data prep allows you to specify what subsets of data you are interested in. You can write the filters, reduce the scope of the data set. Once you start interacting with the data, the Spice engine kicks in. It ingests the data and responds to all the queries really fast. Spice is a technology that we have built right from the ground up. Spice stands for Superfast Parallel In-Memory Calculation Engine. What Spice allows you to do is to collect and compress the data in a columnar way and optimize it for in-memory use. The title Data Scientist is relatively new and has been around for only a few years. It was actually coined in 2008 by data and analytics leads at LinkedIn and Facebook. This title has come to replace data analyst. A data scientist can have formal training in quantitative field, but they can also emerge from any of the fields that has got strong data and computational focus. A data scientist's most basic and universal skill is the ability to write code, but they also have a very solid foundation in maths, in statistics, probability, and even computer science. They work with the complex data sets and they are good at converting masses of unstructured data into structured data, and but most importantly, getting into a form that can be really analyzed. Often they are creative in displaying the information visually and making the patterns they find clear and compelling. Let's look at some of the tool sets that data scientists use to analyze the data. While data scientists can access Redshift data, or they can also leverage Athena, which is serverless and allows you to access data using SQL. After SQL, R is the most commonly programming language used by the data scientist. R is a popular statistical programming language with a number of extensions that support the data processing and machine learning tasks. R provides a rich software development for data manipulation, exploration, including a graphical display. R is easily extended using packages. For example, Shiny Server is a visualization R package that allows you to create interactive dashboards. Similarly, you can install packages in R to query Redshift. For example, you can install the RJDBC package to load Redshift's JDBC driver and then send SQL queries to Amazon Redshift. The difference between the Python UTFs and R in this scenario is that you have to take the data out of the database to do your analysis. You can also write R code using dplyr package to analyze your data in Redshift. First, you have to create a connection to Redshift via R PostgreSQL package. Once R is connected to Redshift, you have the flexibility to add predictive modeling using R's packages. There's also a good big data blog that shows you how to connect R with Redshift in a detailed manner. Athena is an interactive query service which allows you to get results fast and mostly in seconds. Remember, it is not a database, neither a data warehouse. This is for querying data which is stored in S3 and designed to write your queries and give you results in seconds. Athena directly query data from S3, so you don't have to move or load the data anywhere from S3. We want you to query your data in raw format, which can be CSV, TSV, or any other data formats. It can query even the log files which our services generates. For example, the ELB logs, the CloudWatch logs, or the VPC flow logs. And if you convert your data in ORC or Parquet formats, these formats are basically nothing but open source formats which supports columnar data and compression. Then you can even go ahead and lower your query cost to a great extent, and we will discuss the pricing of Athena in next few slides. You can use a few lines of PySpark code running on Amazon EMR to convert your files to Parquet for the best performance and cost. When you create a table for Athena, you are essentially just creating a metadata, and as you run your queries, the schema is applied to the data. The data is then streamed to Athena from S3. It is not copied and there is no ETL which is required. This makes Athena really ideal for customers who are using S3 as the data lake. Athena uses Presto as the underlying querying engine. ANSI SQL supports complex joins, nested queries, window functions, and even some of the most complex data types. We also support partitioning your data in S3 to reduce the amount of data that Athena is scanning, therefore improving your performance and cost. When you write your query, it will go to the appropriate partition and read the data from that partition rather than reading all the data, and hence improving both the performance as well as cost. Athena is designed to be very cost effective. If you're not using it, then there is no charge. There is no hourly charge. You are charged only when you are running your query. DTL queries, like the ones which are necessary to create tables, or the failed queries, are not charged. Also, since we charge you based on the data scan, and suppose you have a terabyte of data. If you compress the data with a 5:1 compression ratio, your data will become 200 GB. Then instead of charging you on 1 terabyte, we will be charging you only for 200 GB of data scan. Now let's go ahead and switch our gears and look at the data engineer role. The difference between a data scientist and a data engineer can really vary depending on the organization. In some organizations, data engineers enable data scientists to do their jobs more effectively. The data engineer gathers and collects the data, stores it, does batch processing or the real-time processing on it, and serves it via an API to a data scientist who can then easily query it, but there can be overlap also. For instance, a data scientist might use the Hadoop ecosystem to serve up the answers to their data questions, and a data engineer might be programming an interactive machine learning algorithm to run over a Spark cluster. In a more general sense, a data engineer working on an analytics platform implements and supports the analytics technologies that give end users timely and structured access to the data. In this slide, we will focus on a data engineer who is using Hadoop and Spark for distributed computing and is connecting to the Redshift using a Databricks Spark Redshift package. In this diagram, a data engineer accessing Redshift using the Spark Redshift package installed on an EMR, which is Elastic MapReduce Spark cluster, in 3 different use cases. In the first use case, the data engineer is using a Spark cluster for ETL and loading structured data in Redshift. In the second use case, the data engineer is loading the data directly from Redshift, enriching it and transforming it and saving it back to Redshift. In the third use case, the data engineer is integrating Redshift as a data source and allowing Redshift to interoperate seamlessly with the other data sources accessible to your Spark cluster. Let's dive deeper into the Spark. Spark provides in-memory processing capabilities and natively supports a large number of programming languages. It includes libraries for popular machine learning algorithms, graph processing, stream processing, and for SQL. Data frames are a fundamental data structure used for structured data processing. The Spark SQL Data Sources APIs provides a pluggable mechanism for integration with the structured data sources of all kinds. Spark users can read data from a variety of sources, such as Hive tables, JSON files, columnar Parquet tables, and many others. It also integrates natively with a large number of external input sources, including Redshift. You can manipulate the data in all of the languages that Spark supports, regardless of how the data is stored. What Spark SQL does is that it makes it easy to join the data from different data sources using a single interface. Spark SQL integrates with third-party sources like Redshift using Spark packages. The Spark Redshift package supports loading of the data from Redshift as well as saving the data back to Redshift. The package allows you to integrate large data sets from a Redshift database with data sets from other data sources also. Now, if you want to read the data from Redshift, say you want to process an entire table from Redshift or process a query which returns a large number of rows in Spark. Under the hood, Spark Redshift executes a Redshift unload command which copies the Redshift table or results from a query to a temporary S3 bucket that you provide. Next, it reads these S3 input files and generates a data frame instance that you can manipulate in your application. Let's see how writing to Redshift works. To write to Redshift, the Spark Redshift library will first create the table in Redshift using JDBC. It then copies the partition data frame as Avro partitions to a temporary S3 folder that you specify. Finally, it executes the Redshift copy command to copy the S3 contents to the newly created Redshift table.
A few years back, in order for engineers to make any sort of change, would take months to roll out. Now it happens sometimes in the order of days. AWS and the cloud enables to do that. I'm Ditesh, Director of Engineering at Grab. Grab is the leading ride-hailing service in Southeast Asia. We do 1.5 million bookings if we are not running. Basically, transportation comes to a standstill. Grab is a platform that fundamentally serves two parties. One side of the market, which is very evident, are the passengers. There's another part of it which is just as important, our drivers. We have got the biggest land fleet in Southeast Asia. Drivers depend on us daily for their livelihoods. With this comes two challenges. Because of tremendous amount of demand, we need to scale, but because so many people depend on us, we need to stay stable. And these are two opposing forces. You can scale easily if you don't have to be stable, and you can be very stable if you don't have to scale. And the answer that came after a lot of reflection on this was we need to address the fundamentals. And a big part of the fundamentals is infrastructure. If we can make sure that our infrastructure is built in a way that just doesn't meet the needs of today, but also meets the needs of the future, it completely changes the type of conversations we have. AWS enables that. All these different components are built to let us scale, but then also be reliable. We started out using the basics, as I would call it. In the second iteration, we kind of expanded the services that we use across the board. In order to support our scaling needs, we need to start thinking about caching layers. So that's where we started using Elastic Cache. Redshift enabled a lot of that big data computation. So our Redshift database is huge. It's massive. Everybody in the company uses it. It's not just the engineers. The product guys use it. The marketing team uses it. The data team uses it. In addition to that, we are doing real-time computation. And in order to be able to do real-time demand and supply matching, we need to have real-time data streams. The end result is this. Our drivers will be told the demand is at this place right now. Because there's high demand, the drivers will be paid more. What we are looking to move towards, though, is even one step further. We want to start building predictive models. In 2 hours' time, this area is going to have high demand. If you want to take advantage of that, move to this area. And the way we can do that is by taking into account multiple factors, building data models around it, and using the infrastructure to compute those models and come up with an actionable item. There are many benefits to being on the cloud. Not having to deal with physical issues, having to go down to a data center at 3 a.m. in the morning to change a failed hard disk or a server that's overheating because the fan has stopped rotating. Companies used to have dedicated operational teams just dealing with this sort of issues day in and day out. And that carries very little value for the organization, and more importantly, it carries very little value for the engineers themselves. Every engineering team and every engineer gets an AWS account. They can run full-blown experiments in their sub-account, and they would find things that might be a problem 3 months from now or 6 months from now. And giving engineers that ability is unparalleled. It's my estimate that we probably saved 30 or 40% of resourcing and manpower that then went to serving our core focus, and our core focus is out-serving our customers. The fact that the team didn't have to worry about that just allowed us to move significantly faster. And in a startup environment, that is make or break.
At Finra, we chose AWS because we wanted to be able to deliver innovation at a much larger scale and much more rapidly to our core business. I'm Saman Michael Farr. I'm the Senior Vice President of Technology at the Financial Industry Regulatory Authority. FINRA is the largest independent regulator of financial markets in the US. We have approximately 4,000 staff, and we have offices throughout the US. We evaluated and moved to AWS Cloud for several reasons. One of them was to get the ability to do better analytics on big data and more extensive analytics and deeper looks at what's going on in markets for regulatory purposes. A second reason we chose to move to AWS was to be able to get better cost effectiveness compared to a private data center. Market volumes can vary easily a factor of 3x during normal operations. So we can expand up and down with the volumes that come in, both in the ingestion pipeline, in the validation, and the normalization. Then, in response to different things that are happening in the markets, we're able to spin up clusters with EMR and apply various query engines, such as Hive, to these pools of data that come in. What we're able to do is allow the regulatory analysts to interactively query multi-petabyte scale data. And in doing so, zoom in on where the potential problem areas are. When you're receiving 75 billion records a day and processing this and surveilling this information, if we can automate this process to the highest degree possible, we can be a lot more efficient. And this allowed us to take this information in and have from the point of ingest to the point at which the data is available for analytics to operate without human intervention to deal with errors, resubmissions, and that type of activity. So this allowed us to redirect our investment from production support and operations to software development and developing better analytics. Because we're able to, on demand, request computing resources, what we're able to provide is a rich set of analytics for our regulatory staff. In January of 2014, we began a 2.5-year project to rewrite, re-implement, re-architect our market regulation systems on AWS. And that project has been going on and has been very successful to date. We have approximately 75% of the systems already in production on AWS, and we're beginning already to realize the benefits. We make extensive use of S3, EMR, EC2, Hive on EMR, HBase on EMR. We also make extensive use of the various other supporting systems around these. When we first started to look at AWS and consider moving to AWS, we weren't sure what the support model would be like. As we've moved through the process and engaged with AWS Enterprise support and the various channels that AWS provides, it's been anything but that. And we've received really the type of support that we would expect and require as an enterprise in moving mission-critical systems to the cloud environment.
So that brings us to the end of this session. And today, if you would like to learn more, you can just go to aws.amazon.com/big-data. Here, you will find information on big data analytics solutions, partners, case studies, and various other technical resources. If you would like to gain hands-on experience with AWS, please watch our instructional videos and explore the self-paced labs. You can also attend our instructor-led classes and learn how to design, deploy, and operate highly available, cost-effective, and secure applications on AWS. You can get more information by visiting our URL aws.amazon.com/training. AWS also has a wide ecosystem of partners to help you focus on your success and take the full advantage of our business benefits that AWS has to offer. Learn more about how APN partners can help you and find the right APN partner for your needs by visiting our AWS APN booth at our partner showcase. Thank you again for attending the session and hope you found it interesting. Do provide us with your feedback and let us know how we can improve the event experience for you in the future.